Hello students and welcome back. So now we are going to talk about the combinational circuit design flow. That means how can we design a combinational circuit in a logical way. So in this video we are going to talk about that how to design a combinational circuit. That means what is the combinational circuit design flow, what are the steps involved in the complete process, and we'll also talk about some standard combinational modules which we will be discussing in this training program. So let us get started. So combinational circuit design flow is a 5-step process. In the first step, we are provided with the system specification. That means we will be given the instruction from the client that I want this system. It should have these many inputs, it should have these many outputs, and the functionality of the system. Once we have the specification, then we are going to create the truth table from those inputs and the outputs, and the truth table will describe the functionality of the system. From the truth table, we are going to obtain the Boolean expressions. Once the expressions are obtained, they may not be optimized, so we are going to optimize or minimize them. Once that is done, then we will transform the Boolean expressions into the logic diagram. In the previous video, we had discussed few of these things independently, but now it's making a sense that how can we relate all of them for the complete circuit design flow. So let us talk about these steps in detail. So first of all, we have the system specification. Here we are going to identify the number of input and the output variables required. The user may not tell those in detail to us, but as a designer, we have to think that what will be the optimum number of inputs and output variables. Once we decide that, then we work on the relationship between these input and output variables. We have to also identify some invalid condition. That means if this particular input is given, then no output can be generated, or this particular output can never be generated. So all of these we have to work on. Next is generating the truth table from those specifications. So we are going to have input variables. We will tabulate them and generate all possible input cases. The general rule is if you have n number of input variables, you are going to have 2 raised to power n test cases. So for each input case, respective outputs will also be written, and we will have a truth table something like this. So what we observe here, that we have 3 inputs, x1, x2, x3, so a total of 8 cases, and we have the value of y. Some of the values are 0, some of the values are 1, and then accordingly we go to the next step. So the next we have is obtaining the Boolean expressions. This thing we discussed in the previous video also, that whenever we have the output value as 1, those cases will be considered as minterms. We are going to take and identify all such cases, and we are going to get a sum of product kind of Boolean expression. So sum of all these minterms will generate the Boolean expression to describe the output function, and we can also identify zeros and get our Boolean expression in terms of product of sum. Both these examples were described in the previous video. So now we have our Boolean expressions with us. What is the next step? The next is to minimize them. The Boolean expressions that we obtain directly from the truth table may not be optimum at all. What is the meaning of optimum? That means when we convert one expression into a gate diagram, how many logic gates are required? Our aim should be to use minimum number of gates. So if there are more literals, that means more variables and more dot and plus sign in your expression, we are going to consume more number of logic gate. So our aim is always to have an optimum Boolean expression. So we need to have these minimum number of logic gates. There are two methods to do that. One is using Boolean algebra postulates and theorems, and the other is using K-maps. Using the Boolean algebra postulates and theorem, we basically work on pen and paper and we start minimizing the expressions by taking something common and then applying the Boolean algebra theorems to get the minimum expression. But that may not give us the minimum result all the times. So then we use the graphical method, and that is K-maps. We are going to share a set of examples and practice problems with you for both these methods in the resource section. Now comes the last step, and that is designing the logic diagram. Once we have the minimized Boolean expression, we are going to map it into a logic diagram. Each product will be replaced by AND gate. When we say replace, that means we are mapping it. A dot in the expression means AND gate in the logic diagram. Similarly, some sign will be mapped with the OR gate, and invert symbol will be replaced or designed with NOT gate. If you have any other gates like XOR, XNOR, NAND, NOR, they can also be used when we convert our expressions into a logic diagram. So let us talk about some standard combinational circuits and modules that we are going to discuss in this training program. We will take arithmetic operations such as adders, subtractors, multipliers and all. We are going to work with shift logic circuits also. That means how can we shift the data. We are going to talk about multiplexers, demultiplexers, encoders, decoders and comparators. So all of them we will be discussing at different stages. And then once we design these modules, we will also use them, multiple modules in a single circuit, to make slightly complex digital systems. So students, now we know little bit about the combinational circuits and how to design them. Let us start working on that. And the first circuit that we are going to make is a full adder, and we'll talk about that in our next video. Keep learning. Thank you.